Welcome to space science. Earth does not end in a single moment. It ends slowly, layer by layer, over millions and billions of years. The sky changes first, then the oceans begin to fade, the continents dry, the air thins, and even the planet's deep interior can no longer protect the world above. In this video, the future of Earth unfolds in time-lapse, from the first quiet signs in space to the final fate beneath an aging sun. If this kind of deep time science fascinates, please like, subscribe, and share the video to support space science. Earth circles the sun at a quiet distance that seems stable when measured against human life. The planet moves through a broad path of dark space, and in that motion the great conditions of the surface appear gentle enough to last. Light arrives, reflects from clouds and ice, sinks into oceans and stone, and leaves again as heat. The balance is never perfect, yet for long ages it remains close enough for air, water, and life to share one world. In the deep future that balance changes, not because Earth suddenly wanders away, and not because the sun abruptly becomes violent, but because ordinary stellar aging slowly alters the flow of energy. The change begins far from any ocean and far above any wind. It begins in the sun itself, and from Earth's distance it first appears as a gradual increase in brightness. The sun is a star powered by fusion, the joining of light atomic nuclei in its core. In simple terms, hydrogen becomes helium, and a small part of mass becomes energy. That energy moves outward through dense solar layers and finally leaves as light and heat. Over immense spans of time, this process changes the sun's internal structure. Helium slowly gathers in the core. The core contracts under gravity, and that contraction raises temperature and pressure. Fusion in the surrounding regions becomes more effective. As a result, the sun grows brighter as it ages, even while it remains the same kind of star for billions of years. Observations of similar stars and models of stellar evolution indicate that this increase is steady on long-time scales. It is not dramatic from year to year. It is almost invisible from one century to the next. Yet over hundreds of millions and billions of years, the added energy becomes one of the main facts that governs Earth's future. From Earth's orbit, the sun still looks calm during this long transition. It rises with the same disk, the same pale edge in haze, the same white glare above cloud tops. Space around Earth remains mostly empty, and the planet still follows the same broad path around the star. The average distance changes only slightly over very long intervals, because orbital motion responds to several gentle effects. The sun loses a little mass through light and solar wind. The stream of particles that flows outward from the solar atmosphere. When a star loses mass, the gravitational hold on orbiting bodies weakens slightly, and their average orbits can drift outward a small amount. Earth's path, therefore, is not perfectly fixed. It slowly expands by a modest degree over time. Yet this outward drift does not cancel the sun's rising brightness. The increase in solar energy is much larger than the slight relief provided by orbital change. At Earth's distance, more energy arrives than before, and the difference keeps accumulating. The future seen from this outer perspective is therefore not a story of sudden collision or abrupt cosmic disorder. It is a slow tightening of radiative pressure on a planet that still appears quiet from space. A radiative balance is the exchange between incoming solar energy and outgoing heat from a planet. When incoming energy rises, the surface and atmosphere must respond until a new balance is reached. Earth does this continuously. Ice cover shifts, clouds change, water vapor rises or falls, Surface brightness changes as snow retreats or dust spreads. At first, these are adjustments within a living climate system. Later, they become steps toward conditions less friendly to complex life. The earlier stage of the end is therefore not destruction in the common sense. It is a long, measured increase in the energy budget of the whole planet. Seen in time-lapse across millions of years, the sunlight over Earth becomes less forgiving. Continents and oceans still turn beneath the same star, but each long interval carries slightly more heat than the one before. Seasons still exist because Earth remains tilted. Day and night still alternate. The moon still circles. The familiar architecture of the Earth-Moon-Sun system continues, and that persistence can make the change seem small. Yet a persistent system can still move toward a new state. Stability in motion does not mean permanence in condition. The orbit stays near enough to its old form that the main signal comes not from mechanics, but from energy. Solar activity also continues during this era, though it is not the central cause of the final trend. The Sun has magnetic cycles, changing sunspot counts, flares, and variations in solar wind. These produce short-term shifts in the near-space environment around Earth. They matter for the upper atmosphere and for magnetic interactions. But on the scale of the far future, they are small ripples on top of the deeper brightening caused by stellar evolution. The broad direction remains the same. More sunlight reaches Earth on average. The near space around the planet becomes the front line of a long planetary transition. From far away, Earth still glows blue and white for a long time. Clouds reflect light, oceans hold dark color, polar regions brighten and dim with ice. Nothing in the distant view immediately reveals how serious the slow increase in solar output will become. That is one reason the future end of Earth is so quiet at first. The planet does not announce it with a broken orbit or a shattered surface. It keeps moving with the old grace of celestial mechanics. It remains a world in order. The danger lies in the order itself, in the dependable operation of stellar physics. This future is supported by strong scientific understanding, though some details remain uncertain. Stellar models consistently show that the Sun becomes more luminous over time. Planetary climate models indicate that even modest long-term brightening can eventually push Earth beyond the conditions that support its present oceans and biosphere. It remains uncertain exactly how feedbacks among clouds, ice, atmospheric composition, and geology unfold across each stage. And different models can shift the timing, yet the overall direction is clear. Earth at this distance does not stay as it is forever. The amount of energy arriving from the Sun slowly rises, and the world must answer. So the first region of the story is not the ground, the sea, or the air. It is the space of orbit itself, the calm ring in which Earth continues its ancient path, while the star at the center grows brighter. In that quiet geometry, the end begins. No mountain falls. No ocean boils in an instant. No sky tears open. There is only a planet moving through darkness, receiving a little more light with every great stretch of time, and carrying that extra light inward toward every layer that will one day change beneath it. Above the weather, and above the bright white tops of ordinary clouds, Earth carries a thin outer envelope of air that is easy to overlook from the ground. It stretches upward into a region where the atmosphere becomes faint, where gases spread far apart, and where sunlight meets the planet before it reaches the denser sky below. In the deep future, as the Sun slowly grows brighter, this high region changes before the lower world fully understands what is happening. The first visible ground signs still remain limited, yet far above them the outer air is already adjusting to a stronger stream of energy. The upper atmosphere includes several layers with different behavior. In simple terms, the stratosphere lies above the troposphere where most weather happens. The mesosphere lies above that, and the thermosphere is higher still, where very energetic sunlight strongly affects the thin gas. Beyond these layers, the atmosphere becomes so thin that particles can travel long distances before colliding. This outer fringe gradually blends into space. These regions matter because they receive the first direct impact from increasing solar radiation, especially the energetic parts of sunlight that break molecules apart and heat the thinnest air. When strong sunlight reaches high atmospheric gases, it can split molecules into atoms. This process is called photodissociation, meaning light-driven breakup. In Earth's upper air, water vapor, oxygen, and other molecules are all affected in different ways depending on altitude and wavelength. In the present era, only limited amounts of water vapor reach the highest layers because the atmosphere below acts as a barrier. Cold regions trap much of the water lower down. In the deep future, as Earth warms over immense spans, more water vapor reaches higher altitudes than before. There, solar radiation breaks some of it apart into hydrogen and oxygen. Hydrogen is very light. Once it reaches great heights and gains enough energy, some of it can escape Earth's gravity altogether. This loss is slow when measured against a human timescale, but a time-lapse across millions of years gives it weight. A few atoms leaving here and there would seem unimportant, yet a planet can lose an ocean one atom at a time if the process continues long enough. The upper atmosphere therefore becomes the first quiet exit route for part of Earth's water. The surface oceans do not vanish in this section of the story, and the ground below does not yet fully show the outcome. But the pathway begins here in the thin air. Energy enters from the sun. Water rises from below. Light breaks molecules apart. The lightest pieces drift towards space. At these heights, temperature behaves in a way that differs from common experience. In the thermosphere, the air can be described as very hot because individual particles carry high energy, yet the gas is so thin that it would not feel hot in the ordinary sense. Heat there is not like a warm stone or a summer wind. It is a measure of particle motion in a near vacuum. As solar brightness increases, this upper region absorbs more energy and expands. The atmosphere swells outward. The outer boundary shifts. Drag-on satellites would change if any still remained, and the planet's gaseous outline would become slightly more extended. This is not a dramatic inflation visible from the ground. It is a subtle thickening of the thin outer veil. Charged particles also play a role. The sun releases not only light but also streams of matter and bursts of energetic particles. In the upper atmosphere, some atoms and molecules lose electrons and become ions, meaning electrically charged particles. This creates the ionosphere, a region important for radio transmission in the modern age and for the interaction between atmosphere and magnetic field. In the far future, a brighter sun tends to strengthen the processes that create and heat this charged region. The exact behavior depends on solar cycles, atmospheric composition, and the state of Earth's magnetic shielding. Observations indicate that solar activity varies naturally across shorter cycles, while the long-term increase in solar output changes the average conditions over vast intervals. It remains uncertain how every detail of upper atmospheric chemistry evolves under far future conditions. But the overall direction is clear. More solar energy means more ionization, more expansion, and a greater opportunity for atmospheric escape. Oxygen in the upper atmosphere also follows a long transformation. Some oxygen remains bound in molecules, while some exists as single atoms at high altitudes. Ozone, a form of oxygen made of 3 atoms, plays a major role in absorbing ultraviolet radiation in the stratosphere below. In the highest layers, intense radiation constantly breaks and reforms oxygen-bearing species. As the atmosphere warms and its chemistry shifts, the balance among these forms changes. The exact future profile of ozone remains model-dependent because it depends on temperature, circulation, water content, and chemical reactions across several layers at once. Yet the upper atmosphere is certain to become a more active chemical frontier as the sun's energy increases. From the ground, these changes remain almost silent. No ordinary observer sees hydrogen slipping away into space. No horizon reveals the slow inflation of the thermosphere. Even the color of the sky, still made mainly by the lower atmosphere scattering light, gives little warning. The upper air does not present its crisis in familiar weather. It works through rarity, radiation, and escape. It is a place where sunlight meets molecules one by one. Earth's magnetic field still offers protection during much of this long era by guiding many charged solar particles around the planet. That shield is not perfect, and it does not block light. It mainly changes the paths of charged particles. So even with magnetic protection, the upper atmosphere remains exposed to the growing brightness of the sun. The shield also channels some particles toward polar regions, where they energize the air and create auroral light. In the deep future, such glows may still ripple at high latitudes for a long time, but their beauty does not alter the larger trend. The outer atmosphere is under increasing pressure from above. This region is therefore the first atmospheric register of Earth's ending. It receives stronger sunlight, warms in its thin way, alters its chemistry, and slowly lets the lightest gases go. The process is patient. It does not resemble collapse. It resembles a leak too slow for ordinary memory, yet too persistent to ignore across geological time. The calm ring of orbit delivers more energy. The upper air accepts it first. In that acceptance, the planet begins to lose what it cannot easily replace. Below the highest thin air, yet still far above the ground, the middle sky carries the long structure of climate. Here the atmosphere is no longer a near vacuum shaped mainly by radiation and escape. It becomes a layered moving body of gas, holding heat, moisture, and circulation. In the deep future, after the outer air has already begun its quiet adjustment to a brighter sun, these middle regions slowly reorganize. The change is not one single storm and not one sudden overturning. It is a gradual remaking of patterns that once distribute warmth and water around the planet. This part of the atmosphere includes the stratosphere and the troposphere beneath it. The troposphere is the lowest major layer, the region where most clouds form and where ordinary weather takes place. The stratosphere above it is calmer in a vertical sense, with temperature behavior shaped strongly by ozone and sunlight absorption. Together these layers govern how heat is moved, where clouds gather, how rain forms, and how the planet releases energy back to space. They are the active skin of climate. When the sun brightens over immense intervals, this skin does not remain fixed. It shifts its temperature, its moisture, and its motion. A warmer world can hold more water vapor in the lower atmosphere. Water vapor is itself a greenhouse gas, meaning it helps the atmosphere retain heat by absorbing some of the outgoing thermal radiation from the surface. This is one of the most important feedbacks in climate science. A feedback is a process that responds to change and then increases or reduces that change. In this case, extra solar heating warms the surface and lower air, which allows more water vapor to remain in the atmosphere, which then strengthens warming further. The principle is well established. The exact path toward the far future state depends on cloud responses, circulation changes, and the timing of ocean and land feedbacks. Yet the broad trend remains clear. More incoming solar energy supports a wetter lower atmosphere at first, and that wetter atmosphere traps more heat. Clouds become more difficult to predict in detail, but no less important. They reflect sunlight back to space, which tends to cool the surface, and they also trap some outgoing heat, which tends to warm it. Their total effect depends on altitude, thickness, droplet size, coverage, and time of day. In the deep future, clouds do not vanish at once. They reorganize along with the circulation of the atmosphere. Regions that once support persistent cloud belts may move. Storm tracks may shift poleward. Some dry zones may expand. Some tropical cloud systems may intensify for long periods before larger instability changes the whole balance. Climate models indicate that cloud feedbacks remain one of the more uncertain parts of long-term planetary warming. It remains uncertain exactly how every cloud regime evolves under extreme future forcing. Yet it is known that cloud changes can either delay or accelerate warming depending on location and structure. The sky remains active, but its familiar distribution of brightness and shadow slowly changes. The large wind systems also adjust. Earth's atmosphere moves because the sun heats different parts of the planet unevenly. The equator receives more direct sunlight than the poles, and the rotating planet turns simple flow into bands, waves, and circulating cells. In the present world, this leads to trade winds, jet streams, rising tropical air, sinking subtropical air, and move-in storm systems in middle latitudes. In a hotter future, those patterns still exist for a time, but they are altered by stronger heat, weaker ice contrast, and changing moisture. Some circulation bands broaden, some wind belts move. The contrast between equator and pole shifts as polar regions lose reflective ice and warm faster. The atmosphere, still orderly in a physical sense, becomes less like the climate that shaped the modern biosphere. The middle sky also grows more vertically extended. Warm air expands. As the lower atmosphere heats, pressure surfaces rise to greater altitude, and the depth of the troposphere can increase, especially in warm regions. This means the active weather layer becomes taller in places. Thunderstorms can reach great heights where moisture and instability support them. A storm in such a world may carry extraordinary energy, not because the laws of weather are new, but because the air holds more water and the surface provides more heat. Yet even repeated severe weather is not the central story here. The larger story is the slow drift of the whole atmospheric machine toward a state that favors heat retention over long-term balance. As warming continues, one threshold becomes increasingly important. If the atmosphere grows warm and moist enough, the upper parts of the lower atmosphere begin feeding much more water upward toward regions where sunlight can break it apart. This is linked to what planetary scientists call a moist greenhouse state. The term does not mean a literal greenhouse made by human hands. It means a climate in which water vapor becomes abundant high in the atmosphere, allowing water loss to space to accelerate over geological time. Observations of Earth's present atmosphere and models of planetary climate indicate that this is a critical stage in the long future of a brightening Earth. The exact timing remains uncertain because it depends on cloud behavior, atmospheric composition, and the interplay with ocean heat transport. Yet the middle sky is where the conditions for that transition are assembled. The visual character of the sky changes with these processes. Haze can become more common in some regions. High humidity thickens the distant air. Cloud tops may rise higher over hot oceans. Dry belts may widen over certain latitudes, leaving larger stretches of hard blue sky above overheated ground. Other regions remain wrapped in repeated cloud, build-up and rainfall for a long interval. There is no single future sky for the whole planet. Climate is uneven. Yet the global mean state continues moving toward greater warmth and a heavier atmospheric burden of water vapor. The stratosphere, too, is changed by what rises from below. Its chemistry depends on light, temperature, and transported gases. More water entering higher layers shifts reactions involving ozone and oxygen compounds. Some parts of the stratosphere may cool or warm relative to others, depending on how radiation and circulation evolve. The result is not simple. Atmospheric layers can respond in opposite directions at different heights, but the integrated effect remains part of one planetary adjustment to stronger sunlight. Thus the middle sky becomes the region where added solar energy is turned into climate transformation. Here heat is stored, moved, delayed, and amplified. Here clouds become uncertain messengers of change. Here circulation remaps the old belts of rain and drought. Nothing has yet reached the final severity that later regions will show. The surface below still holds oceans, continents, forests, and rivers in varying degrees, but above them, in this deeper sky of vapor and wind, the long balance is already being rewritten in air. Across the open ocean surface, the future first appears as a change in light and exchange. The sea still spreads over most of Earth, still gathers the sky into moving colour, still rises and falls under wind and tide, yet the balance at its uppermost layer steadily shifts. More solar energy arrives from above, more heat enters the first skin of water, more moisture leaves it. The sea surface is where sunlight, air, and liquid water meet. And in the long future it becomes one of the clearest regions in which the brightening sun changes the planet. The upper ocean is not a still sheet, it is a thin active zone in constant contact with the atmosphere. Sunlight penetrates it by depth and wavelength. Wind stirs it, and evaporation draws water upward into air. Below this moving surface lies a vast reservoir of heat capacity, meaning the ability to absorb energy without changing temperature quickly. Because of that enormous capacity, the oceans delay extremes for a very long time. They take in heat slowly and redistribute it through currents and mixing. This buffering effect helps preserve Earth's habitability for ages after solar output begins to rise. Yet a buffer is not a barrier. It can slow change, but it cannot cancel a long increase in energy. Seen in time-lapse over millions of years, the sea surface becomes warmer basin by basin. Tropical waters, already warm in the present world, spend longer intervals near temperatures that reduce the margin for marine life. Evaporation strengthens because warmer water sends more molecules into the air. This is a simple physical process. The faster-moving molecules at the surface escape more easily, and the air above can hold more vapor as it warms. The ocean therefore loses fresh water to the atmosphere at an increasing rate. That vapor may later fall as rain somewhere else for a long part of this era, but the exchange itself grows more intense. The sea surface becomes a broader source of moisture, haze, and latent heat, meaning heat carried invisibly in water vapor. Currents continue to move warm and cool water around the globe. On Earth today, this circulation helps prevent the tropics from becoming even hotter and the high latitudes from becoming even colder. Surface currents driven by wind connect with deeper overturning patterns shaped by density differences. In the long future, as the climate system warms, these patterns shift. The exact path remains uncertain because ocean circulation depends on salinity, wind fields, continental arrangement, and the delivery of freshwater from rain, rivers, and ice. Yet the warming surface generally becomes more stratified in many regions. Stratification means that layers resist mixing because warm light water remains above cooler, denser water. When stratification strengthens, the upper ocean mixes less efficiently with the layers below. Heat then stays concentrated nearer the surface for longer periods. This intensifies stress in the region where marine ecosystems live and where evaporation feeds the atmosphere. The chemistry of the surface ocean also changes as temperature rises. Gases dissolve differently in warm water than in cool water. Oxygen becomes less soluble, which means warmer surface seas tend to hold less dissolved oxygen available for marine organisms. At the same time, stronger stratification can reduce the supply of nutrients from deeper layers. The result is an ocean surface that may remain bright with sunlight, yet grow poorer in both oxygen and nutrient renewal across wide regions. Photosynthetic microorganisms still drift in the upper-lit waters for a long time, but the conditions that support complex food webs become more fragile. The issue here is not one single extinction event moving all at once across the sea. It is a prolonged loss of environmental stability at the interface between sunlight and water. Wave fields also change with the air above. Winds continue to shape the surface with ripples, swells, and foam lines. But the sea itself responds differently as the climate warms. Warmer water expands slightly, adding to sea level rise during long intervals when water remains abundant. That expansion is only one part of the surface story, yet it shows how the sea physically answers heat, even before later phases of major loss. Storms passing over warmer surfaces can draw more energy from the ocean. Their local violence may increase in some eras and regions, but the deeper pattern remains broad and slow. The upper ocean gives more heat to the atmosphere and receives more heat from the sun. Each exchange strengthens the next. The color and clarity of the sea begin to change as biology and circulation shift. In some places, stronger surface stratification and altered nutrient transport favor different plankton communities. In others, declining productivity leaves surface waters clearer and more empty. Sediment supply from rivers also changes over immense time as land climates shift. So coastal seas and shallow continental margins no longer look as they once do. Yet this section remains with the open ocean surface. Far from the detailed fate of coasts and inland waters, out here the dominant impression is breadth under heat. Day after day, age after age, the upper ocean receives more energy than the old balance allows. One critical point in this long story is that the surface ocean and the atmosphere become more tightly coupled. As warming intensifies, the warmer the sea surface becomes, the more water vapor it can feed into the lower sky. The more water vapor enters the sky, the more strongly the atmosphere can retain heat. This feedback does not mean the oceans instantly disappear. It means the sea surface takes an active part in amplifying planetary warming. The ocean is not merely a victim of increased sunlight. It becomes a partner in the changing climate through evaporation, heat storage, and vapor supply. Marine life at the surface responds in layers. Sensitive organisms retreat where they can, adapt where they can, and disappear where they cannot. Coral reef systems, already dependent on narrow temperature ranges in the modern era, lose stability long before the final stages of the Earth's end. Floating ecosystems and the shallow life of warm seas face repeated stress from heat, chemistry, and oxygen loss. Yet even as living richness declines, the physical sea remains. Waves still cross long distances. Sunlight still breaks into a scattered path over moving water. The horizon still seems calm from afar. That quiet appearance hides the deep change taking place in the exchange between ocean and air. Over enough time, the surface ocean becomes less a moderator of climate and more a participant in a rising planetary heat burden. It still delays the full severity that later conditions will bring, but it does so while moving toward those conditions itself. The first skin of water cannot remain untouched beneath a brightening star. It warms, stratifies, evaporates, and slowly loses the mildness that once defined the blue face of Earth. Along the edges of the continents, where land and sea meet in shifting lines, the future moves with a slower kind of drama. Coastlines are never fixed even in the present age. Waves wear them down, rivers build them forward, storms cut through them, and tides redraw them twice each day. In the deep future, under a steadily brighter sun and a warmer planetary climate, these margins begin to change more decisively. The open ocean surface has already taken in more heat and given more moisture to the sky. Now the effects gather where shallow water, exposed sediment, and continental rock face one another. Shorelines retreat, low plains transform, and the outer shape of the continents begins to lose the balance that once made it seem familiar. At first, the main changes come through sea level and temperature. When water warms, it expands. When land ice persists in earlier phases of the future, its eventual loss adds more water to the ocean. These processes raise sea level over long spans, and the sea advances over many low coasts. Beaches narrow, barrier islands migrate landward or fragment. Estuaries, which are partly enclosed coastal waters where river water meets the sea, shift their internal balance of salt and fresh water. Wetlands drown where sediment cannot build upward fast enough. Deltas sink and spread apart when river supply weakens or marine intrusion becomes too strong. In time-lapse, whole continental rims appear to soften. The crisp line between land and sea becomes a broad zone of retreat. Rocky coasts respond differently from low sediment shores, but they also yield. Waves continue to break against cliffs, and warming alters the physical condition of the stone. Salt enters cracks. Repeated heating and cooling expand and contract mineral grains. In some regions, where moisture remains available for a long interval, weathering still acts through water and dissolved chemicals. In drier coastal belts, the sea leaves behind crusts of salt as spray evaporates, and those salts widen fractures in exposed rock. Landslides, collapses, and slow undercutting continue, but their pattern is shaped by the longer climatic trend. The sea does not attack a stable continent. It works on land already being transformed by heat. On broad coastal plains, the effect is more gradual and more complete. These are the low regions built by old sediments, often rich in life during the temperate Earth of the past. In the deep future, they become transition grounds between marine invasion and continental drying. As seas rise during the earlier warm stages, these plains are flooded in shallow layers. Bays spread inland. Former river mouths widen into quiet marine arms. Tidal channels move across flats that once support forests. Marshes, or human settlement. The process is not uniform. Some coasts rise tectonically, some sink, some receive sediment, and some are starved of it. Yet the broad tendency remains. Where land lies low, the sea enters. Rainfall patterns, already altered in the atmosphere above, reshape coastal erosion from the landward side as well. Some regions receive stronger bursts of rain for a time, sending more sediment and debris toward the sea. Other regions dry, and their rivers lose the power to rebuild coasts. Where vegetation declines, the ground becomes less stable. Soil is easier to move by wind and sudden runoff. Sediment that once moved through living landscapes now travels through barer terrain. In humid zones, intense downpours cut gullies and transport mud in short, violent pulses. In arid zones, dust and salt begin to dominate the surface. The coastline therefore changes not only because the sea rises or falls, but because the continent behind it stops renewing the shore in the old way. As time advances further, a deeper reversal begins. The warming that first expands the sea and spreads it inland also pushes the planet toward greater evaporation and long-term water loss. The coast enters a strange era in which some regions that are first flooded may later stand beside shrinking seas. This does not happen suddenly, and it does not unfold in one clean sequence everywhere at once. Earth is large, and its basins respond unevenly. Yet over geological time, as water is increasingly transferred to the atmosphere and then slowly lost from the planet through upper atmospheric escape, the total volume of stable surface water begins to decline. Coastal geography then becomes less a matter of marine advance alone and more a record of instability. Ancient shorelines are stranded. New salt flats appear where shallow marginal seas pull back. Former seafloors are exposed to sun and wind. This long transition leaves clear marks in the materials of the coast. Layers of sand, mud, shells, and evaporate minerals build one over another. Evapораtes are minerals left behind when water evaporates, such as gypsum and halite. In enclosed coastal basins and restricted shallow seas, these deposits can accumulate as heat intensifies and evaporation exceeds replenishment. The coast becomes a place where the hydrological balance writes itself into stone. At one time, the sediments speak of rising marine water. Later they speak of concentration, salinity, and retreat. The line between shore and basin no longer carries the old ecological richness. It becomes increasingly mineral and severe. The living systems of coasts fade with this transformation. Mangrove belts, salt marshes, tidal flats, seagrass meadows, reefs, and the nesting grounds of countless animals depend on narrow combinations of temperature, salinity, sediment supply, and water depth. When those combinations shift too far, these systems thin out and break apart. Some migrate for a while, some collapse region by region. Coasts that once act as dense boundaries of life become simpler, more exposed, and less buffered against storm and wave. Biological structure gives way to physical exposure. From a distant view, the continents still look whole for a very long time. Their great masses remain in place, guided by tectonic movement too slow to notice in a single glance. Yet their outlines change around the edges. Shallow shelves flood, and then, in places, later dry. Peninsulas narrow. Island chains connect or disappear. Inland seas open and close according to climate and basin depth. The map of Earth does not stay still beneath a brightening sun. The coast is therefore a region of translation. It receives the oceanic warming from one side and the continental transformation from the other. It turns climate into geography. It records energy as erosion, transgression, salinity, and retreat. The edge of the world does not vanish at once. It loosens, shifts, and redraws itself again and again, until the margins of the continents no longer resemble the patient shores of the earlier Earth. Across the broad surfaces of the continents, away from the immediate influence of the sea, the land carries a different kind of change. Here the future is written in soil, vegetation, and the slow exchange between air and ground. The coast has already begun to shift, and the oceans have warmed at their surface. Now the interior landscapes respond to the same rising energy, but through processes that depend on life as much as on physics. Forests thin, grasslands retreat, and the living skin of the land begins to lose its continuity. The transformation is not sudden. It unfolds as a long weakening of systems that once regulate water, carbon, and temperature. Plants depend on a narrow balance of sunlight, water, temperature, and soil chemistry. In the early phases of warming, some regions experience longer growing seasons and temporary increases in plant productivity. This effect is known from present climate observations, where moderate warming can enhance growth under certain conditions. Yet as the sun continues to brighten over immense spans, the trend moves beyond that limited benefit. Heat becomes excessive. Water becomes less reliable in many regions. Soil moisture declines as evaporation strengthens. The same sunlight that once supports life begins to push it towards stress. Water availability becomes the central constraint, even where rainfall remains for a time. Higher temperatures increase the rate at which water leaves both soil and plant surfaces. This process is called evapotranspiration, meaning the combined loss of water through evaporation from the ground and transpiration from plant leaves. As the atmosphere warms, it can draw more moisture from the land. Plants must either access deeper water reserves or reduce their activity. Many cannot adapt quickly enough to the pace of long-term change. Forests that depend on steady moisture begin to thin. Trees die in place or fail to regenerate. Open gaps spread, and the canopy loses its continuity. Grasslands, which tolerate drier conditions than forests, also shift under increasing heat. Some expand temporarily into former forest regions during intermediate phases, but even these systems have limits. Persistent high temperatures and declining soil moisture reduce the density and diversity of grasses. In many regions, plant cover becomes patchy. Bare ground appears between surviving vegetation. Wind gains more influence over exposed surfaces, lifting dust and fine particles into the air. The land begins to lose not only its green cover, but also its ability to hold itself together. Soil, which forms over long periods through the breakdown of rock and the accumulation of organic matter, depends on life to maintain its structure. Roots bind it. Microorganisms cycle nutrients within it. When vegetation declines, these processes weaken. Soil becomes more vulnerable to erosion by both wind and sudden water flow. In regions where rainfall still occurs in bursts, intense downpours can strip away unprotected topsoil in a short time. In drier regions, wind becomes the main agent of loss, carrying fine material across large distances. The land surface grows coarser and more mineral as the finer components are removed. The carbon cycle also changes as vegetation declines. Plants take in carbon dioxide from the atmosphere during photosynthesis and store it in their tissues and in the soil. When plant cover is reduced, this storage weakens. Carbon that would have been held in living systems remains in the atmosphere or is released from decaying biomass. Over long intervals, this contributes to maintaining higher atmospheric carbon dioxide levels, which in turn support additional warming. This is another feedback, where a change in one part of the system reinforces the original trend. Fire becomes more common in some transitional phases. Dry vegetation and higher temperatures create conditions in which fires can spread over large areas. These fires release stored carbon and further reduce plant cover. Over time, as vegetation becomes too sparse to support continuous burning, fire activity may decline simply because there is less fuel. Yet the legacy of repeated burning contributes to soil degradation and loss of ecological complexity. Landscapes that once cycle through growth and decay become simpler and more fragile. Regional differences remain important throughout this process. Some areas retain pockets of moisture for longer periods due to geography, elevation, or local circulation patterns. Mountain ranges can capture limited rainfall, High latitudes, which begin cooler, may experience delayed transitions compared to equatorial regions, yet the global direction remains consistent. Increasing solar energy raises temperatures across all regions, and the capacity of land ecosystems to adjust is eventually exceeded. As plant cover declines, the reflectivity of the land changes. Surfaces without vegetation often reflect more sunlight in some wavelengths and absorb more heat in others, depending on soil composition and moisture. This alters the local energy balance. In some cases, brighter surfaces reflect more incoming light, providing a slight local cooling effect. In other cases, darker exposed rock absorbs more heat. The net result varies by region, but it does not reverse the global trend driven by the sun's increasing output and atmospheric feedbacks. The land participates in the changing energy balance without controlling it. Dust becomes a more visible feature of the continental interior. Fine particles lifted from dry soils can travel across regions, affecting both air quality and the scattering of sunlight. In the atmosphere, dust can reflect and absorb radiation, influencing temperature locally and regionally. Over geological time, dust deposits accumulate in downwind areas, forming layers that record periods of aridity. The continents begin to carry more of this mineral signal, replacing the biological richness that once defines many landscapes. Animal life follows the changes in vegetation. As plant systems break apart, the complex networks that depend on them also decline. Species that rely on specific habitats lose their range. Generalist species persist for longer, but eventually face the same limits of heat and water. Movement across regions becomes more difficult as continuous habitats fragment. The overall diversity of life decreases, not through a single event but through a prolonged narrowing of viable conditions. From a distant view, the continents lose their deep green tones, brown, red, and pale colours spread across large regions. River valleys still mark the land where water persists, but even these become less stable over time. The surface begins to resemble a patchwork of dry basins, residual vegetation, and exposed soil. The sense of a living skin that moderates climate and stabilizes ground fades. In its place remains a more direct interaction between sunlight and mineral surface. The land surface, once active with growth and renewal, becomes quieter in a biological sense but more exposed in a physical one. It absorbs heat more directly. It releases moisture more quickly when it has any to give. It holds less organic structure. The processes that once buffer the climate weaken, and the planet moves further along a path set by energy from above. The transformation of forests, grasslands, and soil is therefore not only a change in appearance, it is a loss of a key layer in Earth's capacity to regulate itself. Across the interior of the continents, where water once gathers into rivers, lakes, wetlands, and seasonal floodplains, the future takes on a quieter and more final form. The living land has already begun to thin, and soils have started to lose their hold. Now the remaining surface freshwater systems become the central expression of change. These waters do not vanish in a single age. They contract, fragment, and become less reliable. Flow weakens, shorelines pull back. Basins that once shine year after year begin to alternate between brief presence and long absence. In the deep future, inland water becomes less a permanent feature of geography and more a temporary condition. Rivers exist because precipitation falls over land, because gravity pulls water downhill, and because the ground, plants, and air together shape how quickly that movement takes place. In the warmer future, each part of this system changes. The atmosphere can hold more moisture, yet rainfall becomes more uneven in many regions. Some places receive stronger storms but fewer of them. Other places lose sustained precipitation altogether. At the same time, higher temperatures increase evaporation from soils and open water, and they increase transpiration from whatever vegetation remains. This means that even when rain still falls, less of it is available to maintain long river flow. Water is lost more quickly between storm events, and streams that once run throughout the year begin to break into seasonal channels. The upper reaches of river systems respond first in a visible way. Small tributaries, fed by local rainfall or snow in earlier climates, become intermittent. Their channels remain carved into the land, but water occupies them only after short wet intervals. Gravel bars widen, fine mud cracks in the sun. Plants that once lined the banks retreat or disappear, leaving the edges less stable. Without strong roots to bind the margins, flood pulses cut new paths more easily. A river under these conditions is less a continuous ribbon than a sequence of uncertain episodes. In Timelapse, the network of surface flow begins to blink on and off across the continents. Larger rivers persist longer because they integrate water from vast drainage basins. For a long interval, they still cross dry country in broad valleys, carrying the memory of wetter uplands or distant storms. Yet even these great systems weaken as the climate continues to shift. Their annual peaks may remain strong during intense rain events, but their average discharge declines as evaporation rises and tributary support fades. Some rivers lose their connection to the sea during dry phases and end instead in inland basins or seasonal wetlands. Others continue to reach the coast for much longer, but with smaller and more variable flow. The old image of a river as a dependable artery of the land becomes less true with each immense stretch of time. Lakes respond even more directly because they are places where water pauses. A lake persists only when incoming water balances outgoing loss through evaporation, seepage, and overflow. In the future, this balance turns against permanence. Warmer air above the surface increases evaporation. Reduced river inflow lowers water levels. Shorelines retreat over exposed mud and mineral flats. Shallow lakes disappear first because they contain less volume relative to their surface area. They warm quickly, evaporate quickly, and can cross from open water to marsh to salt-crusted basin within geological intervals that are brief compared with the age of the planet. Deeper lakes survive longer, but they too contract unless sustained by unusual local conditions. The chemistry of inland waters changes as they shrink. When water evaporates, dissolved salts and minerals remain behind. This raises salinity, sometimes gradually and sometimes quite rapidly in enclosed basins. Freshwater lakes can become brackish, meaning partly salty, and later hypersaline, meaning much saltier than the ocean. Organisms adapted to one chemical range are replaced by simpler communities adapted to extremes, and eventually even those may fail when the water body becomes too warm, too concentrated, or too intermittent. A lake that once supports layered ecosystems of fish, plants, insects, and birds can become a reflective plain edged by mineral crust. Wetlands and marshes, which depend on shallow groundwater or persistent surface water, are among the most vulnerable of all inland systems. Their existence relies on delicate balance. Too little inflow and they dry, too much evaporation and they become saline. Too much variability and their seasonal rhythm breaks. In the deep future, most wetlands contract or vanish as the hydrological cycle becomes more extreme and less supportive of long-lived freshwater storage. Their disappearance matters physically as well as biologically. Wetlands slow floods, store carbon, and moderate local climate. When they're gone, Water moves across land in shorter, sharper pulses or fails to move at all. Groundwater can delay the visible loss of rivers and lakes for a long time. Water stored beneath the surface feeds springs, seeps into channels, and sustains oases long after surface climates turn harsh. Yet groundwater is not an independent source. It is a reserve built by earlier conditions. If recharge, meaning replenishment from rain and snow, declines over long intervals, the reserve is gradually depleted, springs weaken, artesian flow slows. River reaches once fed from below go dry. Some deep aquifers may persist for very long periods, especially where rock structure traps ancient water, but they cannot maintain continental surface fresh water indefinitely under a brightening sun. The visual transformation of inland water is both subtle and vast. River valleys remain as shapes in the land even when flow is gone. Lake terraces, beaches, and stranded deltas mark older water levels above the shrinking shore. Former channels thread through plains as pale scars. Salt rings spread around receding basins. Dust rises from exposed lake beds where fine sediments dry and fracture. The continent begins to display memory more strongly than motion. Water leaves behind forms that testify to where it used to rest and how it used to move. Regional exceptions can last a long time. High mountain basins, tectonic depressions, and groundwater-fed oases may preserve inland water later than surrounding terrain. Some basins may even experience temporary renewed filling during unusual climatic intervals. But these do not alter the global tendency. As solar energy continues to rise and land ecosystems weaken, permanent fresh water on the continents becomes rarer. Rivers lose continuity, lakes lose volume, wetlands lose resilience. Water that once organizes landscapes into connected living systems becomes fragmented into isolated remnants. In this stage of Earth's future, the inland waters still exist, but they no longer govern the land with their former steadiness. They survive in retreat. They occupy smaller spaces, shorter seasons, and simpler chemistries. Their disappearance is not loud. It happens through lowered levels, longer dry intervals, and the slow conversion of fluid geography into exposed basin floor. The world still contains water, but on land it is becoming increasingly difficult for that water to remain gathered in the open. Where inland waters once remain for long ages, they do not disappear without leaving a record. As rivers weaken and lakes retreat, the land begins to open into broad basins of exposure. These are the low places where water used to gather, where sediments settle grain by grain, where dissolved minerals accumulate quietly over immense stretches of time. In the deep future, after the shrinking of rivers and lakes has already become widespread, these former water bodies pass into a new state. They become dry basins, salt plains, and dust-bright floors under an increasingly powerful sun. The transition is not only a loss of water, it is a conversion of the surface from a liquid landscape into a mineral one. A basin is simply a region lower than the ground around it, a place where water, sediment, and salts can collect. Many basins on Earth are connected to rivers, and some have outlets that carry excess water onward. Others are enclosed, which means water can enter but cannot leave except by evaporation or seepage. These enclosed basins are especially sensitive to warming, because once inflow declines and evaporation rises, the water level falls and the chemistry becomes more concentrated. In the earlier stages of Earth's future, many such basins pass through phases of shrinking lakes and rising salinity. Now, in this later region of the story, the exposed floor itself becomes the dominant feature. When lake water evaporates, it leaves behind what it once holds in solution: calcium, sodium, Chloride, sulfate, magnesium, and other dissolved substances remain after the liquid is gone. They can crystallize into surface deposits or accumulate in shallow layers below the ground. Over time, this produces evaporate minerals, gypsum, halite, and other salt spread as crusts, nodules, veins, and brittle plates across the former bed of the lake. The surface may appear pale, reflective, and nearly level from afar, yet close inspection reveals polygon cracks, lifted flakes, and delicate crystals growing where brine once lingers briefly after rare wet intervals. The basin becomes a place where chemistry stands in the open. These salt flats are not all identical. Some remain hard and dry for long stretches, with a crust strong enough to carry wind-blown sediment over it. Others are more fragile, with wet mud hidden just beneath a thin, bright surface. In some places, the last concentrated pools of brine persist at the lowest points, darkening the otherwise white or beige plain. These pools can still shift with season or climate pulse for a while, but their presence is temporary and unstable. The overall direction is toward concentration, desiccation, and exposure. Water is no longer the organizing element of the basin. Mineral residue is. As the surface dries further, wind becomes one of the main sculptors of the basin floor. Fine particles that settle in old lakes are often made of clay, silt, and precipitated salts. Once dry, these materials are easily lifted into the air if no vegetation anchors them and if crusts break under thermal stress. Dust storms can rise from exposed lake beds and travel across large distances, carrying the memory of vanished water into the sky. This dust changes the color of the horizon, softens distant views, and settles over nearby land in thin, repeated layers. In geological terms, such deposits can build thick sequences over time. In the immediate sense of the landscape, they create a planet that looks increasingly dry, not only because water is missing, but because its former floors are now entering the atmosphere as powder. The thermal behavior of these basins also differs from the wetter landscapes that come before them. Water has high heat capacity, so lakes' moderate temperature changes. Bare mineral surfaces do not. A salt plain can heat strongly by day and cool sharply by night, depending on air conditions and crust properties. This means local climates over dry basins become more extreme. Air near the surface shimmers. Convection, the vertical movement of heated air, develops readily over broad exposed flats. Mirage effects become common where light bends through layers of hot air close to the ground. The basin no longer reflects the sky from liquid water, it distorts it through heat. Some basins reveal older histories as they dry. Former shorelines remain as benches along the surrounding slopes. Delta deposits project into emptiness where rivers once entered standing water. Layers of mud, shell, carbonate, and salt are cut open by erosion and displayed in stepped walls. The ground begins to read like an archive. Each layer records a phase when the balance between inflow and evaporation differs from the phase above or below it. In an earlier age, the basin may hold a deep lake. Later it may become shallow and saline. Later still it may dry almost completely, only to refill briefly in a wetter interval. By the time the future reaches this section, the long-term trend has become too strong for permanent recovery. The archive remains, but the water that writes it no longer stays. Biological life in these basins is reduced to extremes. As salinity rises, only organisms adapted to very concentrated water can endure for a time. Microbial mats may form in shallow brines. Salt-tolerant species can persist in narrow chemical windows, yet as conditions continue to intensify, even these specialized forms lose ground. The basin surface grows simpler, the visible signs of life become sparse or absent across large areas. What remains is largely physical and chemical structure: crusts, cracks, sediment fans, evaporate bands, and dust plumes. The former margins of the basin also change. Without stable shorelines or marshes, the transition from low plain to upland becomes sharper in some places and more diffuse in others. Alluvial fans, built by sediment spread out where streams leave steeper terrain, may advance across the dry floor during rare runoff events. These pulses do not restore the basin as a lake. Instead, they deliver gravel, sand, and mud that later dry and are reworked by wind. The basin becomes an arena where water appears briefly only to leave more mineral and sediment behind. This region of Earth's future is quiet in soundless ways. It holds wide light, little shade, and almost no softness. Former inland seas and lakes no longer cool the air or support continuous food webs. They act instead as sources of salt, dust, and reflected glare. Under the stronger sun, the contrast between high land and low basin sharpens because the low places reveal the concentrated remains of what the planet has lost. Water gathers there for millions of years, then leaves. And what is left behind is a white and brittle memory. Dry basins and salt plains therefore mark a turning point in the inward path. The continents are no longer shaped mainly by living cover and flowing fresh water. In these exposed depressions, the surface begins to belong more fully to mineral processes. Evaporation, crystallization, cracking, and wind now dominate. The disappearance of water is no longer only measured by reduced rivers or shrinking lakes. It is measured by the presence of salts where water once stands, by dust rising from former depths, and by the widening of surfaces that no longer hold anything fluid at all. With the low basins dried and bright with salt, the surface of the continents begins to show a more direct relationship with the sun. The living cover has thinned, inland waters have retreated. Much of the exposed ground now lies under open sky with little protection from heat. In this region of the story, the focus moves from water and life to the crust itself, the outer solid skin of Earth made of rock, sediment, and weathered material. The crust does not melt at the surface in this stage, and it does not break apart all at once. It changes through expansion, contraction, cracking, chemical alteration, and the slow reorganization of minerals under more severe conditions. The future reaches the point where sunlight is no longer filtered mainly through forests, wetlands, and broad lakes. It arrives on stone. The crust is a thin outer shell compared with the whole planet, yet it is the layer on which climate leaves its marks most visibly. It contains igneous rocks formed from cooled magma, sedimentary rocks built from particles and chemical deposits, and metamorphic rocks altered by heat and pressure within the planet. At the surface, these rocks are usually modified by weathering. Weathering is the breakdown and alteration of rock through physical stress, chemical reaction, and biological activity. In the earlier Earth, water, roots, freezing, thawing, and microorganisms play major roles in that process. In the hotter future, the balance among these agents changes. Biological weathering weakens with the decline of ecosystems. Water-driven weathering becomes more limited across broad dry regions. Thermal stress and salt action become more important at the surface. Thermal stress is simple in principle. Materials expand when heated and contract when cooled. If a rock surface experiences repeated temperature swings, its outer layers and inner parts do not always respond at the same rate. This difference builds internal strain. Over time, grains loosen, thin layers detach, and fractures widen. In a world with more exposed bedrock, fewer plants, and stronger surface heating, this process becomes increasingly common, day after day across immense intervals. Rock faces absorb energy under a brighter sun. They release it after dark. The repeated cycle does not need dramatic violence to be effective. Given enough time, it peels stone apart from the outside inward. Salt action adds another form of mechanical change. Salts left by evaporating water can enter cracks and pores in rock. When those salts crystallize or expand under changing humidity, they push outward on the surrounding material. In dry coasts, former lake margins, and saline soils, this can become a strong agent of breakdown. Stone that once endures under milder conditions begins to lose its surface grain by grain. Corners round off. Thin outer shells flake away. Fracture networks spread through cliffs and outcrops. The surface becomes rougher in some places and more powdery in others. Chemical weathering continues, but it takes on a different pattern as water grows scarce. Many chemical reactions that alter rock require liquid water or moisture films. These reactions include the dissolution of minerals and the formation of clays. In wetter parts of Earth's earlier history, chemical weathering can be intense, especially in warm, humid climates. In the hotter and drier future, large regions lose the steady moisture needed for continuous reaction. This means some chemical pathways weaken, yet heat still accelerates reaction rates when water is present, even briefly. Rare storms, short-lived films of moisture, and deep humidity trapped in soils or cracks can still drive bursts of alteration. The result is a more intermittent style of chemical change, less constant than before, but not absent. Different rock types respond differently to this future. Granite, made largely of quartz and feldspar, can resist some forms of breakdown for long periods, yet feldspar minerals gradually alter under chemical attack, and grains separate under thermal stress. Basalt, common in volcanic regions and oceanic crust, contains minerals that can weather relatively quickly when water is available, though under dry-hot conditions its surface may develop hardened crusts before deeper alteration proceeds. Sedimentary rocks show great variation. Sandstones may crumble where cement weakens. Shales can split into thin sheets. Carbonate rocks such as limestone react readily with acidic water, but when liquid water becomes scarce their dissolution slows, and they may instead stand as bare, pale surfaces subject to heat and cracking. The future crust is therefore not uniform. It becomes a patchwork of responses shaped by mineral content, texture, and exposure. Soils that remain on the land continue to thin or harden depending on local conditions. In some places, repeated drying and heating produce crusted surfaces that resist infiltration when rare rain does arrive. Water then runs off quickly rather than soaking in. This increases flash erosion in channels and leaves the surrounding ground even drier. In other places, fine materials are simply removed by wind, exposing coarse gravel or bedrock. The surface evolves toward extremity, either sealed and hard or stripped and loose. Both outcomes reduce the ability of the ground to support renewed biological cover. Color becomes one of the plainest signs of this change. Exposed crust displays reds, browns, blacks, greys, and pale mineral whites according to iron content, oxidation state, and rock type. Oxidation is a chemical process in which minerals react with oxygen, often producing reddish iron compounds. In dry landscapes where rock surfaces remain exposed for long periods, these colors become more prominent, without dense vegetation to soften the view. The mineral character of the continents is laid open. Earth from above still shows clouds and remnant water in some regions, but much of the land begins to resemble an older, harsher planet beneath the same orbit. Surface roughness also changes the way heat is handled. Bare rock and gravel absorb sunlight, store heat, and re-radiate it into the air above. Some surfaces reflect strongly, especially salt-rich or pale sedimentary plains, while darker volcanic terrains absorb more. Yet at the scale of the whole crust, the important fact is exposure. The insulating, moist, and living cover that once mediates energy exchange is diminished. The crust speaks more directly to the atmosphere. It warms quickly under daylight, cools after dark, and contributes to near-surface instability in the air. There is still weather in this world, and weather still shapes rock. Wind abrades surfaces with dust and sand. Rare rains carve gullies and transport sediment downslope, but these are now acting on a landscape already transformed by long desiccation and heat. Valleys remain, mountains remain, plateaus remain, yet their surfaces are increasingly defined by physical endurance rather than biological partnership. The crust shows its own architecture more clearly because so much that once covers it has been lost. This stage does not yet enter the deeper subsurface, where buried water, trapped gases, and hidden chemistry respond in slower ways. It remains with what lies open beneath the sun. Here the future becomes mineral at the surface. Rocks crack, salts expand, thin skins of altered material loosen and fall away. The continents retain their shape in the large sense, but their faces harden, bleach, oxidize, and fracture. The end of Earth, seen at the level of the crust, is not a spectacle of sudden ruin. It is a patient exposure of stone to relentless light, until the ground itself becomes the clearest record of a world losing its softness. Beneath the exposed rock and hardened soils, below the ground that cracks under heat and sheds dust into the air, the planet still holds hidden reserves. These are not great open seas or broad river systems. They are pockets, films, and slow-moving stores of matter buried within the upper crust. Water remains in pores between grains, in fractures inside stone, in chemically bound form within minerals, and in deeper aquifers that remember older climates. Carbon remains trapped in sediments, in carbonate rocks, in organic residues buried long ago, and in gases enclosed beneath pressure. In this region of Earth's future, the focus moves below the visible surface into the shallow underground, where heat, dryness, and time begin to alter what the crust still stores. The shallow subsurface is a boundary zone between climate and geology. It is where rainwater, when it still falls, enters the ground. It is where roots once reach, where microbes still persist longest after surface ecosystems fail, and where chemical exchange continues after the land above has become harsh. In the earlier Earth, this zone acts as a buffer. It stores moisture after storms, feeds plants through dry periods, and allows dissolved minerals to move slowly through sediments and rock. In the deep future, as temperatures rise and surface water becomes rare, that buffering role weakens. The ground is recharged less often. Moisture penetrates less deeply in many places. The underground begins to live on inherited reserves. Buried water does not all behave the same way. Some of it exists as soil moisture, thin films around grains and particles that can be lost quickly to evaporation or taken up by roots. Some exists as groundwater filling connected pores and cracks beneath the water table, the level below which the ground is saturated. Some remains trapped in isolated pockets that exchange only slowly with the surface. As surface climates become hotter and drier, the shallowest stores are lost first. Soil moisture becomes brief and unreliable. The upper ground dries more completely between rare wet intervals. This allows heat to travel downward in new ways because wet soil and dry soil conduct and store heat differently. The upper crust becomes more thermally responsive to the stronger sun above. Deeper groundwater persists longer. Aquifers, meaning underground layers of rock or sediment that hold and transmit water, can preserve immense volumes for long periods. In some regions, these waters are ancient, recharged under climates very different from those of the far future. They rise at springs, seep into valley bottoms, and feed the last dependable wet places long after rain-fed systems fail. Yet such reserves are not renewed indefinitely. Recharge declines as rainfall weakens or becomes too episodic, and as hardened dry surfaces shed water rather than absorbing it. Over geological time, even deep aquifers begin to empty or become increasingly isolated. The hidden water table falls, springs fail, moist valleys lose their underground support. The planet does not only lose visible water, it also loses what is stored out of sight. Some water remains locked into minerals themselves. Many rocks contain hydrated minerals, meaning minerals whose crystal structures include water or hydroxyl groups. Clays, some sulfates, and certain metamorphic and volcanic minerals can all hold water in bound form. This water is not free to flow like groundwater, but it is part of the planet's shallow inventory, under increasing heat, especially where burial, pressure changes, or local geothermal conditions matter. Some hydrated minerals can dehydrate and release part of their water, in the uppermost crust heated only by surface climate. This process is limited and often slow, yet it remains an important reminder that the dry future Earth still contains water not visible as liquid. It is stored within matter itself, hidden inside the chemistry of stone. Carbon beneath the surface also follows several pathways. Carbonate rocks such as limestone and dolostone store enormous amounts of carbon in mineral form. Organic carbon remains buried in sediments, ancient soils, coal-bearing layers, petroleum source rocks, and residual biological matter from long earlier ages. Some gases, including carbon dioxide and methane, are held in porous formations or trapped beneath impermeable layers, as the surface becomes hotter and drier. These stores do not all release at once. They respond according to burial depth, temperature, pressure, and contact with moving fluids in many shallow regions. The decline of a life above means less new carbon enters the soil. Organic turnover weakens. Soils become poorer in organic matter and more mineral in character. The shallow ground gradually loses one of its main living functions as a carbon reservoir. Chemical weathering within the subsurface also changes. In a wetter world, groundwater dissolves minerals, transports ions, precipitates cements, and alters rock over long periods. It can widen fractures in soluble rocks, create caves in limestone, and transform volcanic glass and feldspar into clays. In the hotter future, these reactions become more restricted by water supply. Where liquid water still moves, heat can accelerate reaction rates. But the zones of active alteration become smaller and more discontinuous. Some old underground cavities dry. Mineral-rich waters leave cements and crusts behind as they retreat. Salts accumulate not only on the surface but also below it, filling pores and reducing permeability, the ability of rock or sediment to let fluids pass through. The shallow crust becomes more sealed in some places and more fractured in others. Gas movement through the ground gains importance where dryness opens pathways. As soils shrink, crack, or lose organic structure, gases can move more directly between the atmosphere and the shallow subsurface. Carbon dioxide produced by residual microbial activity or by decomposition after rare wet pulses can escape more quickly. In some basins, heated ground may release trapped gases episodically through fractures. The quantities and timing are uncertain and vary greatly by geology. Observations from dry earth environments today indicate that arid soils can still exchange gases strongly with the atmosphere after brief moisture events. It remains uncertain how these pulses scale under far future planetary conditions, but the shallow underground is unlikely to remain chemically still. Even in apparent dryness, slow exchange continues. The last microbial communities persist here longer than on the exposed surface. Microbes can survive in pore water, within salt crystals, inside rocks, and in deep sediments where temperatures remain tolerable and some chemical energy remains available. Their world is dark, small, and slow. They do not restore the biosphere above, but they mark the persistence of life in protected niches long after the open continents have become hostile. As groundwater declines and temperatures rise, these habitats shrink. Salinity increases in residual pore waters. Nutrient pathways break down. Oxygen availability changes from place to place. The deep future shallow crust becomes a narrowing refuge. Mechanically, the ground settles and stiffens in new ways as hidden water is lost. Sediments compact. Clay-rich layers shrink when they dry. Surface subsidence can occur where groundwater withdrawal, natural or climatic, reduces support in porous formations. Cracks propagate upward or downward through drying sediments. The land above may appear still, yet its near-surface structure is being rearranged by the slow departure of fluids from below. This inward region therefore reveals a planet living off stored inheritance. The surface has already lost much of its water, life, and softness. Beneath it, the remaining underground reserves continue to delay total desolation, but only for a time. Water falls through fractures less often. Aquifers recharge less. Soil carbon fades. Mineral-bound water remains trapped until deeper processes touch it. Hidden gases shift through drying ground. The shallow crust is no longer a generous buffer between climate and rock. It becomes a thinning vault of remnants, gradually emptied by heat, time, and the fading exchange between Earth's surface and what lies just below it. Below the shallow reservoirs of buried water and trapped carbon, the planet continues into a deeper structural world that moves too slowly for ordinary sight. Here the crust is no longer only a surface of exposed stone, dust, and fractured ground. It becomes part of a larger engine made of plates, faults, rising magma, descending slabs, and the slow transfer of heat from the interior toward the surface. In the deep future, even as the continents dry and the surface loses much of its water. This tectonic planet does not simply stop, it continues its ancient motion, yet the world above it has changed so much that tectonic activity begins to appear in a different setting. Volcanoes, uplift, rifting, and crustal recycling persist, but they act on a surface that is hotter, drier, and less able to soften or hide geological force. Plate tectonics is the long movement of large pieces of Earth's outer shell over the weaker material beneath. These plates carry continents and ocean floors. They separate at spreading centers, where new crust forms from rising magma. They converge at subduction zones, where one plate descends beneath another. They also slide past each other along transform faults. This motion is driven by heat loss from the interior, by gravity, and by the sinking of cold, dense slabs into the mantle. In the present Earth, plate tectonic shapes mountains, ocean basins, earthquakes, and volcanic arcs. In the far future, the same system still operates for a very long time. Earth does not become geologically dead in the near term of solar brightening. Its outer shell continues to shift while the climate above it moves towards severe decline. The continents themselves remain mobile on geological timescales. Their coastlines and surface conditions have already changed, but the deeper plates continue to carry them across the globe. Ocean basins open and close, mountain belts rise and erode. Supercontinents may assemble and break apart over spans of hundreds of millions of years. These large rearrangements influence climate by altering ocean circulation, rainfall patterns, and the distribution of land across latitudes. In the future Earth, such tectonic geography still matters, but its influence is increasingly overshadowed by the sun's rising output. Tectonics can shift the local and regional setting of heat and aridity, yet it cannot reverse the planetary trend towards surface uninhabitability. Subduction remains one of the most powerful parts of this deep outer system. Where oceanic crust sinks into the mantle, it carries water-bearing minerals, sediments, and carbon-rich material downward. Some of that material is released again through melting and volcanism. In this way, plate tectonics participates in long-term recycling of water and carbon between the surface and the interior. In the hotter future, this recycling still continues, but the surface reservoir feeding it has changed. There is less liquid water available at the surface over time, fewer active biological contributions to sedimentary carbon, and altered erosion patterns across the continents. Subduction zones therefore continue to function, but the character of what they receive from above gradually shifts. Sediments become drier, more mineral, and less rich in organic matter. The great recycling system endures, yet its inputs reflect a planet in decline. Volcanism also persists. Magma still rises where plates separate, where mantle plumes reach upward, and where subduction adds water and lowers melting temperatures in the mantle above descending slabs. Volcanoes continue to build cones, plateaus, and ash layers. Lava still cools into basalt and other igneous rocks. Gases still emerge from vents and fissures, including water vapor, carbon dioxide, sulfur compounds, and other volatiles. In a wetter Earth, these emissions interact strongly with oceans, ice, vegetation, and active weathering systems. In the future drier Earth, the same eruptions occur against a barer background. Ash falls on dry ground instead of wet forest. Lava enters shrinking seas or dry basins. Volcanic gases enter an atmosphere already transformed by solar forcing. The eruptions are still geologically significant, but their surface consequences are filtered through a harsher climate. The balance between tectonic carbon release and tectonic carbon removal also changes in meaning. On present Earth, the carbonate-silicate cycle helps regulate climate over immense timescales. Carbon dioxide released by volcanoes enters the atmosphere, dissolves in rainwater, contributes to rock weathering, and is eventually locked into carbonates that may later be subducted and recycled. This cycle depends on liquid water, exposed silicate rocks, erosion, transport, and sedimentation. In the deep future, as surface water becomes scarce and weathering systems weaken, this stabilizing cycle loses effectiveness. Volcanic carbon dioxide can still be released, but the pathways that remove it from the atmosphere become more limited across broad regions. The overall climate is then governed less by a strong geological thermostat and more by the overwhelming rise in solar energy. Tectonics still speaks, but the sun speaks louder. Mountain building continues to reshape the continents where plates collide. Uplift raises rock into thinner air, creates topographic barriers, and exposes fresh mineral surfaces. In earlier climates, these mountains can draw moisture from passing air and feed rivers, glaciers, and chemical weathering. In the hotter future, uplift still creates relief, but the hydrological response is reduced. Some mountain belts may preserve local pockets of cooler or wetter conditions longer than nearby lowlands, simply because elevation changes temperature and circulation. Yet even these refuges are temporary within the larger planetary trajectory. Peaks continue to rise and wear down, but their snow, ice, and river systems cannot remain indefinitely under a brightening sun. Earthquakes remain part of this tectonic world. Strain accumulates in the crust as plates move, and it is released along faults in sudden ruptures. These events continue regardless of whether the surface above is green, barren, flooded, or dry. In the far future, earthquakes still break rock, shift landscapes, and trigger landslides. Their local effects may be severe, but they are not the main driver of Earth's end. They are signs that the planet's outer shell remains active even while the surface climate has moved beyond the conditions familiar to life. Rifting, where continents stretch and begin to split, also continues on its own schedule. Valleys open, fault blocks tilt, magma rises through thinned crust. New ocean basins may begin where old continents fracture apart. Such processes show that Earth, as a tectonic body, remains dynamic. The outer solid shell is not freezing into immobility during these stages. Instead, it continues its long habit of renewal and destruction. But the renewal is geological, not biological. Fresh crust may form while the surface loses habitability. New volcanic landscapes may appear while rivers disappear. Geological vitality and surface livability are no longer aligned. This region therefore presents a planet in two different states at once. At the surface, heat, dryness, and loss dominate. At the scale of plates and upper mantle interaction, motion and recycling continue. Earth is declining as a habitat, but not yet as a geophysical system. That distinction matters. The end of Earth for life does not require the end of tectonics. A world can remain internally restless long after its surface becomes hostile. The deeper outer shell still bends, breaks, rises, sinks, and melts. It carries continents toward new arrangements. It feeds volcanoes and draws old crust downward. It moves with a patience far older than climate. Yet the setting in which it now acts has changed almost beyond recognition. No broad forests soften fault scarps. No great inland waters fill tectonic depressions for long. No stable coastlines endure beside volcanic arcs. The same tectonic engine continues, but it works under a hotter sun and over a surface stripped of many of its former companions. In that contrast, the planet shows one of its quietest truths. It can remain geologically alive while becoming biologically lost. Beneath the moving plates and below the faults, volcanoes and subduction zones of the outer shell, Earth enters a deeper and broader domain of slow motion. This is the mantle, the thick rocky layer that extends from the base of the crust to the boundary of the core. It is solid in the ordinary sense, yet over immense spans it flows. That flow is not like a river or a liquid sea. It is a creeping deformation driven by heat, pressure, and gravity. So slow that a mountain range can rise and vanish while the mantle beneath it only slightly changes shape. In the deep future of Earth, long after the surface has dried, the atmosphere has shifted, and life has retreated from open land. The mantle still works. It remains one of the main engines by which the planet loses its internal heat and reshapes its outer parts. This region of the story turns inward to that hidden circulation. The mantle is made mostly of silicate rock, rich in oxygen, silicon, magnesium, and iron. It becomes hotter and denser with depth. Near the top, beneath the tectonic plates, some parts are stiff enough to help support the moving shell above. Deeper down, high temperature and enormous pressure allow the rock to deform slowly under stress. This long deformation is called convection, when heat causes material to rise and sink in broad patterns. In simple terms, warmer and slightly more buoyant mantle tends to move upward over time, while cooler and denser mantle tends to sink. The process is complex, not a neat set of circles, but the basic result is a planet that transports internal heat upward through vast solid motion. That internal heat comes from several sources. Some of it is leftover heat from Earth's formation, when collisions, compression, and early differentiation leave the young planet extremely hot. Some of it comes from radioactive decay, the natural breakdown of unstable elements such as uranium, thorium, and potassium within the planet. These elements release energy over long periods, helping maintain internal warmth over billions of years. However, Earth gradually cools. Heat escapes through the crust, through volcanic activity, and through the general upward transfer carried by mantle motion. The future mantle is therefore not a static reservoir. It is a system slowly spending a finite thermal inheritance. In the present Earth and for a very long time into the future, mantle convection supports plate tectonics. Rising regions can contribute to seafloor spreading and volcanic hotspots. Sinking slabs from subduction zones descend into the mantle and may reach great depths, carrying cooler material downward. These slabs alter flow patterns around them. The mantle is not chemically or thermally uniform. Some regions are cooler, some hotter, some more depleted in easily melted components, and some more enriched. This patchwork matters because it shapes where melts form, how easily rock deforms, and how effectively heat is moved. In the far future, although the surface has become far less hospitable, the mantle continues to follow these deep rules. It does not answer directly to the drying of the continents above. It answers to heat, density, and the long mechanical memory of the planet. Even so, the mantle of the future is not identical to the mantle of the past. Because Earth continues to lose heat, the average thermal state slowly changes. Convection may become less vigorous over immense intervals as the interior cools, though not in any abrupt way during the stages already described. Slabs still descend, hot material still rises, partial melting still occurs where pressure drops or water lowers the melting point, yet the overall engine is gradually aging. The pace of heat loss is not constant, and models differ in detail because the mantle is difficult to observe directly. Seismic studies of present Earth reveal its structure through the way earthquake waves travel, and laboratory work helps estimate how mantle minerals behave under deep conditions. These lines of evidence indicate that Earth remains internally active for billions of years, while also confirming that the deep engine slowly weakens as heat drains away. It remains uncertain exactly when plate tectonics might finally cease, because that depends on mantle temperature, water content, crustal strength, and feedbacks between surface and interior. What is clear is that the mantle's future is one of continued motion under gradually declining energy. Pressure shapes this region at every depth. Rock deep in the mantle is compressed so strongly that minerals take forms different from those found near the surface. Olivine and pyroxene, familiar from some upper mantle and volcanic rocks, transform under greater pressure into denser crystal structures. These transformations affect how seismic waves move and how buoyancy behaves inside the planet. They also mark boundaries within the mantle, especially between the upper mantle and lower mantle. The future mantle keeps these internal layers. It remains a structured interior, not a simple mass of hot stone. Heat flow through the mantle is uneven. Some zones send hotter material upward in narrow or broad upwellings. Mantle plumes, where they exist, are thought to be columns or regions of anomalously hot material rising from deep levels. They may feed long-lived volcanic hotspots. Other areas are dominated by the downward pull of cold slabs. The combined effect is a restless but slow interior architecture. In the deep future, hotspot volcanism may continue in some form, and large volcanic provinces may still arise where conditions allow. Such events could alter parts of the surface and atmosphere locally or globally for intervals. But within the larger fate of Earth, they become episodes within a longer decline governed increasingly by solar evolution and internal cooling together. The mantle also stores water, though not as open liquid reservoirs. Water can be held in trace amounts within mantle minerals, especially in the upper mantle and transition zone, bound into crystal structures. This deep water influences melting behavior and rock strength. It lowers melting temperatures in some contexts and may help support tectonic activity by weakening parts of the mantle and lithosphere, the rigid outer shell, in the future. Deep water remains part of the mantle system even after the surface has lost much of its own. Earth therefore keeps part of its water inventory hidden far below, integrated into minerals and melts. The presence of this deep water matters because it links the mantle to the history of subduction and to the long capacity of the planet to remain geologically active. At the base of the mantle, near the boundary with the core, conditions become more extreme still. Temperatures are very high. Pressure is immense. Seismic evidence suggests that this boundary region contains complex structures, possibly including chemically distinct materials and zones where heat transfer is especially important. This deep boundary helps control how heat from the core enters the mantle and how mantle flow organizes above it. It is a zone of exchange between two major layers of the planet, though their materials remain separate in large part. The mantle carries that heat upward, and in doing so it continues the long outward journey of Earth's internal energy. What appears from the surface as a static planet is therefore supported by a vast moving interior, the dried continents, exposed crust, and retreating waters above all rest on rock that is slowly turning over under pressures beyond ordinary imagination. The mantle has no weather, no sky, no seasons, and no open life. Its changes are measured not in storms or years, but in the rise and fall of thermal structures across hundreds of millions of years. Yet this slow motion matters profoundly. It lifts crust, feeds magma, recycles old plates, and gradually exhausts the heat that once makes Earth so active among rocky worlds. In this inward step, Earth is seen as an aging convective body, still alive with deep motion, still sending heat upward, yet no longer at the youthful intensity of its earlier history. The mantle continues to move beneath a surface that has already lost much of its former balance. It does not save that surface, and it does not stop for it. It works according to deeper timescales, carrying the planet's inner warmth upward, one slow deformation at a time, while the long cooling of the world proceeds below everything that has already fallen silent above. Below the mantle's slow circulation lies the metallic heart of the planet, divided into an outer core of liquid iron-rich alloy and an inner core that is solid under immense pressure. This region is hidden more completely than any other. No direct sample reaches it. Its structure is known through earthquake waves, laboratory experiments, theory, and the measured behavior of Earth's magnetic field. In the deep future, after the surface has dried, after the continents have hardened, and while the mantle still carries heat upward in slow motion, the core continues its own long evolution. It remains the source of one of Earth's most important invisible protections, the magnetic field. Yet this protection is not permanent. Over immense time, as the planet cools and its internal gradients change, the field is expected to weaken and eventually fade. The outer core is a deep shell of liquid metal, composed mainly of iron with significant nickel and lighter elements mixed within it. The inner core, deeper still, is solid because the pressure is so high that even great heat cannot keep the metal molten. The boundary between them is not fixed forever. As Earth loses heat to space through the crust and mantle, the inner core slowly grows. Liquid metal at the center freezes onto it, releasing both latent heat and lighter components into the surrounding outer core. Latent heat is energy released during a change of state, in this case from liquid to solid, without a change in temperature. These released energies help drive motion in the outer core. That motion matters because it powers the geodynamo, the process by which moving electrically conductive fluid generates a magnetic field. The geodynamo depends on convection in the liquid core. Heat escapes from the core into the mantle above, as some regions of liquid metal cool, and as differences in composition develop during inner core growth, the fluid becomes buoyant in some places and denser in others. This creates motion. Earth's rotation organizes that motion into patterns that support large-scale magnetic field generation. The field produced is not perfectly steady. It wanders, shifts in strength, and occasionally reverses polarity, meaning magnetic north and south exchange places. These reversals are known from the magnetic record preserved in rocks. They show that the magnetic field is dynamic, not fixed. In the future, the field likely remains variable for a very long time, but the overall capacity of the core to sustain it is tied to the planet's cooling history. The magnetic field extends far into space and forms the magnetosphere, a region where Earth's magnetic influence deflects many charged particles from the Sun. It does not block ordinary sunlight. It mainly affects the paths of energetic charged particles carried by solar wind and by solar eruptions. This protection helps reduce the rate at which the atmosphere is stripped by direct particle interaction, though it does not stop atmospheric change driven by heating and chemistry. In the earlier future, when the upper atmosphere begins to warm and lose hydrogen, the magnetic field still provides significant shielding. As the deep future advances, that shield becomes increasingly important because the surface atmosphere and water inventory have already been weakened. Yet the shield itself depends on a core engine that cannot run forever. Earth's core continues to cool over billions of years. The exact pace is uncertain because it depends on thermal conductivity, composition, the efficiency of heat transfer through the mantle, and the detailed history of inner core growth. Observations indicate that the magnetic field exists now because sufficient energy remains available to drive convection in the outer core. Models of planetary evolution suggest that as Earth ages further, the conditions that sustain strong convection eventually diminish. If the heat flow out of the core becomes too small, or if the balance of thermal and compositional buoyancy changes too much, core motion may no longer be vigorous enough to maintain a strong dynamo. At that stage, the magnetic field weakens and can collapse into a much smaller remnant or disappear as a global shield. It remains uncertain exactly when this happens. Different models produce different timescales. But the broad expectation is that the dynamo does not persist indefinitely. A weaker magnetic field changes the relationship between Earth and space. Charged particles from the Sun can interact more directly with the upper atmosphere. Atmospheric escape can become more efficient for some species under some conditions, especially when combined with a brighter Sun and a more expanded upper atmosphere. The field is not the sole controller of atmospheric loss, and some unmagnetized planets still retain atmospheres under the right conditions, while some magnetized planets can still lose them. The outcome depends on many variables, including gravity, atmospheric composition, solar radiation, and particle environment. Even so, a declining magnetic shield removes one of the protections Earth long possesses. The exposed upper atmosphere becomes more vulnerable to particle-driven erosion and chemical disturbance. In a world already moving towards sterility, this loss deepens the trend. The core also affects the mantle above through heat flow across the core-mantle boundary. If the mantle removes heat efficiently, core cooling continues and convection can remain active. If mantle heat transfer changes, the core responds over long intervals. This means the future of the magnetic field is linked not only to the core itself, but also to the ongoing behavior of the mantle. Earth is a connected interior. The deep metal and the deep rock evolve together. The dried surface above may seem separate from this hidden interaction, yet part of the fate of the atmosphere still depends on how these inner layers exchange energy. Within the core, the conditions are extreme beyond ordinary comparison. Temperatures likely rival or exceed those at the surface of the present Sun, while pressure reaches millions of times atmospheric pressure. Under these conditions, iron behaves in ways explored only through theory, seismic inference, and high-pressure experiment. The inner core may have complex structure, with different growth patterns or crystal alignments in different regions. Seismic studies suggest anisotropy, meaning wave speeds vary by direction, which implies internal organization in the solid metal. The outer core may also have layered behavior near its top, or complex flow influenced by heat and composition. These details remain active areas of research. Observations indicate structure and change, yet it remains uncertain exactly how fine-scale patterns in the core evolve through deep time. Those uncertainties do not alter the main point. The magnetic shield depends on fluid metal motion, and that motion ultimately depends on an energy source that declines. On the surface, the fading of the magnetic field would not appear as a single dramatic event visible in one instant. The compass, if one still existed, would grow less reliable over long ages. Auroral light might behave differently as particle paths change. Radiation conditions in near space would intensify. The upper atmosphere would face a harsher particle environment, but the bare continents and shrinking waters below would already tell much of the story. The weakening of the shield would be another quiet subtraction, another invisible support removed from a planet already losing many of the features that once make it habitable. The core therefore represents both endurance and limitation. It remains active long after forests fail, long after rivers contract, long after coastlines redraw themselves. It keeps generating protection from hidden motion in metallic depths. Yet that endurance is not endless. Cooling continues. The inner core grows. The dynamo ages. The shield weakens. Earth's future is not only a surface decline under a brighter sun. It is also an interior aging in which one of the planet's great invisible defenses gradually spends itself. In this inward region, Earth is seen not as blue ocean, cloud, or rock, but as a sphere of moving metal carrying memory of its hot origin. That deep motion still reaches outward as magnetism, still pushes back against the charged breath of the sun. But over immense time, even this resistance softens. The planet's metallic heart continues to turn, yet its gift to the surface becomes less certain. And the old magnetic shelter that once helps preserve the air above Earth slowly approaches its own end. By the time the future reaches this stage, Earth's surface is no longer a place of stable exchange among ocean, air, rock, and life. The outer air has already changed. The climate system has passed through deeper instability. Inland waters have retreated. The continents have hardened, and the hidden reservoirs below have thinned. The tectonic engine still moves beneath, and the core still ages in darkness. Yet above them the surface enters a final open condition. It becomes a world increasingly sterilized by heat, dryness, radiation, and chemical severity. This sterilization does not mean that every atom is burned clean, or that every surface becomes molten. It means the open exterior of the planet can no longer support lasting biology as Earth once does. The ground, air, and remnant waters move beyond the tolerances that make the old biosphere possible. The central force remains the same one that begins the story. The sun continues to brighten as it ages. This increase in luminosity means more energy reaches Earth's orbit even after the slight outward drift caused by solar mass loss. Over immense spans, the climate is driven toward conditions in which the oceans are no longer stable in their old form. Surface temperatures rise high enough that evaporation becomes relentless over broad regions. Water vapor becomes abundant in the atmosphere. Strengthening heat retention, in the long run, hydrogen escape to space continues to reduce the total water inventory of the planet. The exact timing of each threshold remains uncertain in detail, because cloud behavior, atmospheric composition, and geological feedbacks all affect the path. Yet observations and models indicate that Earth eventually crosses into a state where the surface is far too hot for complex life, and where stable surface water becomes rare or absent. At this point, the surface atmosphere has changed not only in temperature but also in structure. A moist greenhouse state, once an approaching threshold, becomes a defining condition or gives way to even more severe dryness after major water loss. In a moist greenhouse, high atmospheric water vapor allows large-scale photodissociation in the upper atmosphere and sustained escape of hydrogen. As the water inventory diminishes over geological time, the atmosphere can then evolve toward a hotter but drier state, in which much of the planet's former water has already been lost. The sky above such a world is not necessarily dark or cloudless everywhere. Some cloud layers may still form for long periods in certain regimes, and haze may persist in others. But the broad planetary balance no longer favors a living hydrological cycle distributed across land and sea. The atmosphere becomes more a medium of heat transport and chemical loss than a shelter for life. Open surface water, where it still appears briefly or locally, becomes unstable. Shallow ponds or remnant seas evaporate rapidly. Brines can persist longer than fresh water, because dissolved salts lower vapor pressure and can delay complete evaporation. But these brines are hostile and temporary on the largest timescales. Even if rare refuges endure in unusual topographic or subsurface settings, they do not restore planetary habitability. The surface as a whole is no longer organized around the presence of long-lived liquid water. Without broad oceans and lakes to moderate climate, daily and regional temperature extremes become more severe across exposed ground. The buffering memory of water is mostly gone. The chemistry of the surface becomes harsher as moisture declines. Salts accumulate in soils and basins. Oxidized minerals spread across exposed rocks. Ultraviolet radiation reaches the ground through an atmosphere no longer shaped by the old balances of ozone, moisture, and biological gas exchange. The precise future abundance of ozone remains uncertain because it depends on the evolving chemistry of oxygen-bearing species, water vapor, temperature, and solar ultraviolet output. What is clear is that the surface environment becomes more exposed and less moderated. Radiation, heat, and desiccation act together. A living cell on open ground would face the combined strain of broken membranes, damaged molecules, and the absence of stable liquid water. The decline of life proceeds unevenly but decisively. Complex multicellular organisms disappear from most regions long before the final sterilization is complete. Plants lose the water balance needed for growth and reproduction. Animals lose both habitat and thermal safety. Marine ecosystems collapse as oceans overheat, deoxygenate, and retreat. Microbial life persists longer because microbes can tolerate wider chemical extremes and can occupy protected niches, salt-tolerant microorganisms, heat-tolerant forms, and communities inside rocks or below the surface may endure for long intervals after the visible biosphere has vanished. Yet even these survivors face narrowing options as temperatures rise and water availability falls. Sterilization at the planetary surface therefore arrives as a shrinking map of survivable niches until the open exterior itself becomes effectively lifeless. The visual character of Earth changes profoundly in this stage. From space, blue areas contract or disappear except where reflected haze or mineral surfaces mimic brightness once associated with water. Cloud cover may still exist, but it no longer signals the old global engine of ocean evaporation and rain-fed renewal. The continents appear broader, more exposed, and more mineral in tone. White salt expanses, red oxidized terrains, dark volcanic fields, and pale dust belts dominate the view. The poles no longer hold the stabilizing ice that once reflects sunlight and supports strong climatic contrast with lower latitudes. Earth remains a planet with an atmosphere and a solid surface, but it no longer resembles the living world known from its long Middle Age. Weather still occurs, though in a transformed sense. Winds move across hot plains, dust rises from former basins, convective storms may still form where heat and residual moisture interact, but such events no longer feed a generous water cycle. They become local expressions of an atmosphere under stress rather than chapters in a stable climatic rhythm. Rain, if it falls, is exceptional or regionally confined. Runoff is brief. The ground receives water only to lose it again. The surface does not recover between these episodes because recovery requires continuity, and continuity is gone. The rock record of this era would be severe and distinctive. Evaporate deposits become widespread in places where brines concentrate and vanish. Wind-blown sediments build thick layers over dried basins and plains. Weathering crusts form under repeated heating and chemical alteration. Carbonate formation driven by biological systems ceases at the surface, while abiotic mineral processes dominate. Fossil evidence of the once rich biosphere ends below these layers, marking a transition from a biologically sculpted planet to a physically and chemically sculpted one. The surface becomes an archive of loss. Uncertainty remains in the details of how the last surface microbes disappear. Some may survive surprisingly long in deep pores, within salts, or beneath translucent minerals that filter harmful radiation while allowing limited energy to enter. Observations of modern extremophiles indicate that life can endure in places far harsher than once imagined. It remains uncertain exactly how long such protected lineages could persist on future Earth. Yet even this uncertainty sits within a clear boundary. The open surface becomes sterile first, and eventually the protected margins narrow beyond durability. Earth ceases to function as a biosphere-bearing planet. This sterilized world is still Earth in a geological sense. It still rotates. It still orbits the sun. The mantle still convects below, and the core continues its long evolution. Volcanoes may still erupt, faults may still move, the atmosphere may still shift and thin, but the old partnership among liquid water, moderate temperature, and life has ended. The surface is no longer a place where biological complexity can begin again or return easily. It has become too hot, too dry, too exposed, and too depleted. In this region of the inward path, the end is no longer a forecast hidden inside slow feedbacks. It stands openly on the ground and in the sky. Earth's surface has crossed from difficult habitability into terminal hostility. The planet is not yet physically destroyed as an object in space, but as a living surface world it is finished. What remains is stone under intense light, air carrying heat and loss, and the last quiet traces of a once blue planet passing into a state where the surface itself keeps no life at all. At the innermost point of this long path, the story no longer concerns one region of Earth's surface or one layer of its atmosphere. It concerns the whole planet as an object moving toward its last physical condition under the final aging of the sun. The surface has already become sterile. The waters have largely been lost. The air has been altered by heat, escape, and chemical change. The interior still holds motion. Yet none of these continuing processes can preserve Earth as a world in any familiar sense. Now the question becomes narrower and more severe. What finally happens to the planet itself when the sun leaves its long, stable middle age and begins the last major transformation of its life? The sun does not shine forever in the same state. During most of its life, it remains a main sequence star, powered by hydrogen fusion in its core. Over immense time, that core fuel is gradually consumed. Helium builds up. The core contracts under gravity and grows hotter. The outer layers respond. Eventually, the sun leaves the main sequence and expands into a red giant. In this phase, its outer atmosphere extends far outward. Its luminosity rises greatly, and the inner solar system is exposed to conditions far beyond anything in the earlier parts of Earth's future. This transformation is supported by stellar physics and observations of similar stars. It is not sudden on a human scale, but in the long history of planets it marks the final turn. As the sun expands, Earth's environment changes in several ways at once. Solar luminosity becomes far greater than during the earlier brightening that already sterilizes the surface. The planet receives an enormous flux of energy. Any remnant surface materials that still preserve traces of earlier conditions are driven into more extreme thermal states. Rock temperatures rise far beyond those of the already hostile world that comes before. Surface minerals can decompose, melt locally, or vaporize depending on composition and exact conditions. The atmosphere, already thinned or transformed by long water loss, faces intense heating and possible large-scale escape. Earth is no longer merely uninhabitable. It is being forced toward physical dismantling at the surface. At the same time, the sun loses mass through stronger stellar winds. A stellar wind is the flow of particles from a star into space. As the sun sheds mass, its gravitational pull weakens somewhat, and the orbits of the planets can expand outward. Earth's orbit therefore is expected to drift away from the sun to some degree during the red giant phase. This outward motion offers partial relief in geometry, but it does not guarantee survival in physical detail. The outcome depends on more than simple distance. It also depends on tidal interaction and drag within the extended outer atmosphere of the giant sun. Tides are gravitational distortions that can transfer energy and angular momentum between bodies. As the Sun swells and Earth orbits in the altered gravitational field, those interactions become important. This is where uncertainty remains significant. Models agree that the Sun will expand greatly and lose mass. They also agree that Earth's orbit will move outward somewhat, but it remains uncertain whether that outward drift is enough to keep the planet entirely beyond the Sun's expanded outer envelope. Some models indicate that Earth may be engulfed by the red giant Sun. Others suggest that orbital expansion might keep it just beyond the deepest reach of the swollen solar photosphere, the visible outer layer of the star, while still exposing it to extreme tides and drag in the solar atmosphere above that layer. Even in scenarios where Earth is not fully engulfed at first contact, the planet could spiral inward because drag and tidal forces remove orbital energy. The uncertainty lies in the details of solar mass loss, solar radius evolution, and tidal physics. The broad conclusion is clearer than the exact pathway. Earth's final physical end is governed by solar expansion so severe that survival as an intact temperate world is impossible. If Earth is engulfed, the process is not like a small stone dropped into a flame. The Sun's outer layers during the red giant phase are enormously extended but very diffuse compared with solid matter. Even so, the temperatures and drag are enough to erase any remaining atmosphere, melt and vaporize the crust, and strip the planet of its former structure. The solid body would interact with hot stellar gas, while tidal stresses and friction act on its orbit. Over time, Earth would lose integrity as a recognizable rocky world. It could be broken down, vaporized in large part, or absorbed into the Sun's outer envelope, contributing its material to the star. If Earth avoids deep engulfment for a time, it does not return to safety. The surface would already be molten or near molten across large regions under the immense solar flux. Silicate materials, the rocks that make up much of Earth's crust and mantle, can begin to melt at high temperatures, and volatile elements would be lost rapidly. The atmosphere would be stripped to residual heavy species, if any remain at all. Oceans and hydrated minerals would have long since ceased to preserve significant liquid water. A planet in such a position would resemble a scorched remnant, perhaps with magma oceans or extensive molten regions, orbiting just beyond a swollen star. Tidal forces could still decay the orbit. Solar wind and radiation would continue to erode the surface and any gaseous envelope. Survival in this state would mean only temporary persistence as a damaged object. The interior of Earth would also respond. Intense external heating affects the thermal gradient through the crust and upper mantle. Surface melting alters the way heat escapes from below. The old distinction between a cool surface and a hot interior is partly erased as the outside itself becomes furnace-like. Convection in the mantle and any remaining tectonic behavior would no longer shape the surface in the earlier way. The core would continue to exist while the planet remains intact, but its magnetic field would matter little against the overwhelming physical forcing from the giant Sun. Earth's deep interior, once the source of volcanic renewal and magnetic shielding, becomes irrelevant to the question of a long-term planetary survival. After the red giant phase reaches its peak, the Sun will later shed its outer layers and leave behind a white dwarf, a dense stellar remnant roughly the size of Earth but containing much of the Sun's mass. Planets that survive at safe distances may continue orbiting this remnant. For Earth, however, the key uncertainty lies earlier. During the giant phase, it remains uncertain whether Earth survives as a partially stripped rocky remnant in a wider orbit, whether it spirals into the Sun and is destroyed, or whether it is engulfed and vaporized more directly. Observations of white dwarf systems show evidence that planetary material can survive in altered form around dead stars and can also be disrupted and accreted later. This supports the idea that final planetary outcomes can be complex, yet complexity does not imply hope for Earth as a world. By this stage, all habitable identity is already gone, so the last physical image of Earth is not one of blue cloud bands or dark oceans under a moderate sun. It is a remnant confronting stellar old age. Perhaps it is drawn inward through the giant atmosphere and dissolved into hot gas. Perhaps it lingers briefly as a glowing, dust-stripped rock above the solar surface before tides and drag take it. Perhaps part of its mass survives longer as debris or altered mantle material in a changed orbit around the white dwarf left behind. Observations indicate that stars like the Sun end in this general way. It remains uncertain which exact final path Earth itself follows. The uncertainty is real, but it exists within a narrow frame. The planet does not remain whole and unchanged. At the innermost end of the story, Earth is no longer understood as a landscape, a climate, or even a biosphere. It is understood as matter in the reach of stellar evolution. The outer regions have already fallen silent. The inner ones continue only until the star that governs them enters its last vast expansion. Then the planet meets the limits set not by weather, ocean, crust, mantle, or core alone, but by the aging of the Sun itself. The end of Earth, seen in time-lapse, concludes not with a single dramatic instant, but with a long narrowing of possibilities until only remnant or destruction remains under the final light of an old star. The long motion comes to rest in thought before it could ever rest in matter. Earth begins as distance, light, air, water, soil, stone, and hidden fire, and each layer answers the same slow command from an aging sun. The answer is never hurried. It passes through the highest atmosphere as loss, through the middle sky as warming, through the seas as rising heat, through the coasts as retreat, through the continents as drying, through the crust as exposure, through the underground as depletion, and through the deep interior as endurance that cannot finally protect the world above it. What remains to the end is process. Light arrives, heat moves, matter changes form, water lifts, breaks, escapes, rock cracks, oxidizes, and outlasts the living cover that once softens it. In this final quiet view, the planet is still beautiful in a stripped and distant way. Salt plains shine where lakes once lie. Bare mountains hold their shape above dark basins. The atmosphere, though altered, still wraps the globe for a time in colour and haze. Even the deep unseen engine continues its slow work beneath a surface already lost to life. Earth does not end in confusion. It ends by following the same laws that once make it fertile. The same stellar physics that allows warmth also carries excess. The same geology that recycles the crust cannot stop the sky from changing. The same water that nourishes continents can only remain while temperature allows it. At last the world becomes remnant, then uncertainty, then memory in matter, whether Earth is swallowed, stripped, or partly preserved as a damaged relic. Its long middle age is over long before the final solar expansion arrives. The oceans, forests, clouds, and living soils belong to one interval only. That interval is vast, but not endless. The planet continues after life, and the star continues after the planet, and the silence that follows is only the natural stillness of time moving on.